I have the pleasure to introduce Craig Mundie. So Craig is the president of Mundie & Associates. Before that, he was the co-executive chairman of Bridgewater Associates. And before that, actually, he retired from Microsoft as the chief research and strategy officer. So I had the pleasure of meeting Craig last night and understanding that, not only from his bio, you would know that he understands technology really well. Like, clearly, he's an expert on technology. But what I actually learned last night is that not only is he an expert on technology, he's also a great teacher. So in 15 minutes, he taught me more about quantum computing than I think I've ever known. And I took a year of PChem, so that's pretty exciting. And so it looks like we're ready and the demo's ready, so I'm gonna not quite ready, okay. So I learned multiple different approaches to quantum computing, which was pretty exciting. And I think it shows his skill as a teacher. And today actually is going to show us some additional new technology. So you won't hear about quantum computing, but if you ask him on the side, he'll let you know all about it. Thanks.
See if that's any better. Oh, yeah. It's rare that I have to move it up. What I'd like to do today is kind of do a three-part talk. And the first part is going to be a very quick summary of the path that we've been on from what I'll call statistics to artificial general intelligence. And tell you a little bit about where I think we are in that path, and in a sense, I'm not that far different than Dan in some regards. And then the second part, I'm going to show you a demonstration live, assuming everything works well, of a holographic presentation of a CAT scan, and I'll explain, the interest I have in that. And then I'm going to bring the two things together at the end and tell you why, if the kind of technology I'm going to show you on the holographic imaging is really to be used broadly. Unless we can get some machine intelligence to help us, it'll not be available to everyone. So, and just for the record, I just borrowed these images from the Wikipedia topics on each of these. So each image doesn't represent anything that you need to understand. It's just to give you a mental hook, to think about what each stage in this evolution has looked like. And it turns out statistics is kind of mathematics in its foundations, and it goes back 2,500 years. And so those great brains that we've been talking about in the last hour have been doing a lot of this kind of analytical thinking and finding different ways to express it. Probability distributions or these kind of descriptive maps. And we learn a lot by that and have for a long, long time. But the next thing that we did, and frankly this started about 75 years ago, which I'll point out coincides with the arrival of digital computing, and we started to move toward modeling and simulation. We wanted to be able to find ways to take our understanding of the mathematics, if you will, of many things, and get the computer to help us understand problems in ways that we hadn't been able to do. So, I mean, this is an example, very trivial one, of saying, if you want to know how to compute pi, how could you estimate it? And this is just an example that if you do a Monte Carlo simulation and you randomly put spots in there and you color them in and outside of a circle, it ends up you get a perfect representation of pi, so as many digits as you want to run that simulation. So as computers got faster and faster, we found more and more granular ways to emulate what we thought was happening in the real world. And then we came up with lots of clever ways to code these up and to put them in decision trees. And notably, I'll say the state of the art of this you might think of as expert systems. And the way I think about an expert system at a variety of scales is it's kind of as far as we've gotten trying to capture human understanding of a particular problem and write it down in code. And that's what programming computers has been about for about 70 odd years, was trying to take something we thought we understood and find a coded representation of it where the computer could then do that. But we have been learning, certainly in the last 10 or 20 years in the field of computing, that, man, some of these problems that we'd like to solve and where the computers are getting more and more powerful, we just actually don't know how to represent this stuff in code. It's just too hard. And so we went back also to something that had its genesis almost exactly at the same time, about 75 years ago, which was the idea of simulating neural networks. And this is sort of the genesis of machine learning, which you could say is a step along the path to a more generalized form of artificial intelligence at the asymptote. And these actually have come about in two ways. One way was we actually took all the things that Dan showed you the pictures of, the neurons, and we actually tried to write computer models of the neurons. And so, the neurobiology people would tell us, well, this is how I think that neuron works, and the computer people would dutifully code that up, and then we'd stitch them together, and as the computers got bigger and bigger, we could, make bigger and bigger networks, and people said, wow, this is really going to be great. This computer will be just doing like, what humans do in no time. And basically that didn't work so well. And in part, what we know now, when we look back, is the reason it didn't work too well was what you're really doing is you're training. And to train, you have to have something to train on. And relative to the complexity of the things that we think are interesting to model or compute this way, we didn't have a big enough computer, and we didn't have enough data. And we didn't know that at the time, and we kept working hard at it. And people came up with more and more sophisticated ways. They said, well, hey, maybe just emulating the biology isn't the right way to do it, but that neural network idea, that sounds pretty good. So let's just make artificial neural networks that don't really try to mimic biology per se, but they kind of function the same way. And we made a little progress with that, and people would come up with all kind of clever ways to do that. But basically, in, I'll say, the mid-'80s, everything we tried to apply these things to, whether it was character recognition or handwriting recognition or voice or imaging, whatever it is, they would all get to about 85 or 90% error rate, not error rate, but I mean fidelity. And then, but the error rates, were 15% or 10%. And it turns out if you have that high an error rate, these things just have no real utility. And it's like reading a sentence or a paragraph that had 100 words in it, and you say, well, I'm just going to arbitrarily leave out 15 words. I hope you got the meaning right. And so because of that, everything just sort of went into stasis in this. The field was kind of dormant. And then in ways that I think have surprised people, while this domain was sleeping, so to speak, the world of the internet and the hyperscale computational facilities and the diffusion of this into all your pockets, televisions, and everything else you use in your life had two effects simultaneously. One is it created a boatload more data. And so that data problem we had back 20, 30 years ago suddenly went away for a very large number of domains. And to be able to simultaneously let literally hundreds of millions of people, for example, do an internet search or watch Netflix or whatever your passion of the day is on the internet, the companies doing this stuff built monstrously big computer systems of a form that were actually able to be applied to these kind of tasks. Because just like, as Dan said, you got 86 billion of these neurons, which sounds big, but actually by computers these days, that's not very big. And so these things are running around, and we made these really big computers. And basically, machine learning was really unleashed when the academics who had been always pursuing this realized that those guys doing the internet stuff at hyperscale had a boatload of data and really big machines. And that came together. And this tremendous progress over really just the last 10 years had that as the big driver. So now what happens next? Well, deep learning is sort of the name given most popular to this. And here I just borrowed a little clip from a web page of DeepMind, which is a Google company that is now sort of famous for the use of their deep learning system to play Go. And one of the things that I think is really fascinating is how, and if you haven't looked at this problem, is how this evolution of Go playing in this machine went in two stages. The first stage was they said, well, obviously the best way to learn how to play Go is to take all the games played by the world's best Go players and train the machine on that. So they did that. It didn't actually take all that long. And sure enough, they sat down and played the world's reigning champion and just beat him hands down. But then they went away and said, yeah, well, I wonder if that's really the best way to learn how to play Go. And so they then built a machine that took the same basic concept, but all they did was give the machine the rule book for Go and no human games. And they put two of these machines there to play each other. And in a matter of a couple of weeks, by essentially that little pi estimation thing, that sort of Monte Carlo simulation, just think of that scaled up hugely, where every dot isn't a placement in that formula for pi. Every dot is a game of Go that it randomly played. So it started with board positions, and then it would play itself, two machines. It could play a few million games a day. And starting with nothing but the rule book and trying everything it could, just randomly, in a few weeks, it not only learned how to play Go, but it beat the other machine 100-0 in their first match. And so now all the human players are looking at the Go played by this machine and saying, wow, we never even thought of that, all right? And there's now, that whole group is now moving forward into an evolved way of humans thinking about how to play Go that thousands of years of Go play by people, all these 86 billion neurons, never actually found. And so I think this is an unbelievably important step in that you could say there's two ways to come at really complex problems. One is to say, take the best that humans know and either try to replicate it or maybe extrapolate from it. And the other is to just say, could you describe what the problem is? And then, because the computer is so much faster, interestingly, Dan talked about the 40 hertz clock rate of the human. That's it, 40 hertz, okay? So basically the problem with humans is they're just carbon, all right? And if you really want to make circuits that are fast, you don't want to make them out of carbon, and at least not the carbon like humans are made out of. And so when we've built these machines out of other materials, we don't have clock rates that are 40 hertz. We have clock rates that are basically 40 times 10 to the 8th hertz. And that's why it can play millions of games per day, and humans could play a few. And so the real question is, as we take this concept forward now, what's it going to mean? But sort of what are some of the challenges? So a few I listed, the last 3 bullets up here. There's a few problems with this deep learning thing. One is, as Dan said, this is just a little neuronal system, maybe a big neuronal system. It doesn't understand anything. And importantly, now, it can't explain anything. Of course, neither can each of the human subsystems. So yes, there is something that humans can do where they think they can tell you why they did what they did. They can make an attempt at it. In reality, they don't do such a good job. And in fact, if you ask them now what happened some time before and why they did it, they probably wouldn't tell you the same thing that they did at that moment. But it's a problem for humans right now to think they want to put a lot of their trust in these machines when they want to ask the machine, well, why? And it's really good at this thing. Like the Go champion really would love to have asked the AlphaGo Zero machine, but why did you do that move? And of course, the machine can't explain that. And so that's a bit of a problem. So because of that, people are now moving forward in what's called causal machine learning. And this is the attempt to actually sort of combine this idea of modeling and simulation of some form with this type of learning, such that there's some basis of explaining why that all, why it might do what it does. And that's sort of young at this point, but I think an important line of research. The other thing that's really different about humans at this more meta level than these computers today is that the computer doesn't do any transfer learning. And what people mean by that is the ability to say, look, if I've experienced something as a human, and I show you something I haven't seen before, you use everything you know as a referential basis, and therefore the amount of stuff I have to explain to you for you to understand this new thing is pretty small. That's called transfer learning. So machines today don't do any transfer learning because even though people, you could say, as Dan said, are sort of trying to systematically organize all these little, separate neuronal machines, there's no architecture. And I would argue, and this is just my own sort of philosophical view of this now, that the real question for me is on this evolution is whether or not the people doing the computing and the assembly of these expert systems on the way to artificial general intelligence are sort of making the same mistake that the first version of Go did, which is they thought the humans really understood it. And so they're just trying to make the machines operate the way the humans do. So the question is, how much do we have to bootstrap these machines such that we could really just kind of give them an example of this and therefore tell them in broad form what the rules of the game are, and then let it play the game among itself perhaps, or with a little interaction with humans in order to figure that out. So that's sort of a prelude to this next step of the talk, which is my idea about applying deep learning in medical imaging. And in particular, I want to accelerate the extraction of holographic models from traditional medical scans. Now, let me tell you why I decided to get into this. Last November, out of the blue, we discovered that my wife had bladder cancer. And, she embarked on the normal treatment, best normal treatments in the world. And I embarked on a parallel path to figure out what could I do with all my friends in the scientific community to increase her odds. And I have done quite a few things. But one of the things that happened is very early in this process, they went in to do a resection of the tumor. It was bladder cancer, as you'll see in a minute. And because of that, her kidney couldn't drain on the left side because the tumor had grown over that ureter. And so part of the goal was to go in, resection the tumor so we could do genomic and proteomic and other analysis of the tumor to guide the treatment, but also to insert a stent so that her kidney could drain. So they went through this procedure, and it didn't go as planned. And in fact, what happened is they came out and said, well, we found the tumor, got the section of the tumor out, but we never could find the exit of the ureter. And I said, well, why not? He says, well, after we got in there, we just decided, discovered that your wife's is anatomically unusual. And it was unusual in a form where, in a sense, you begin to realize that the doctors, as well trained as they are, and have been given all these CAT scans to think about, they're really just trained to go in there with their scope, look around and say, okay, left ureter, I go in here, I hang a right at 45 degrees, I look around up there, it's supposed to be there. Well, if it isn't there, they have a problem, and particularly if it's very difficult to find because there's a tumor around there too. So she had to have 2 additional surgeries, just to deal with that problem. Now, what I knew even then was that she was facing what was going to become a major surgery down the road, which would be half robotic and half manual. And I'm sitting here saying, if she's anatomically unusual and it affected even this little procedure, when they get in there, they're going to do all this massive reorganization of things, won't that be a problem? So I said, what can I do about that? So I decided to increase her odds of success by developing a holographic model of my wife's midsection, her internals, and to offer this to the surgical team to plan her surgery in advance of the operation. At this scale, as far as I know, it's never been done before. There's lots of small things where people have done some of this surgical planning, but nothing like this. Now, it turns out I called some friends I have in Cleveland, and I'll explain in a moment, and they agreed to adapt a product, if you will, called HoloAnatomy to this task, and to do it quickly, but importantly, they had to do it all by hand. So what I want to do now is just play like a 3-minute video, just straight off the web, which is by Case Western in the Cleveland Clinic. Now, the significance of this, and why could I call these people? 4 years ago, Toby Cosgrove, who runs the Cleveland Clinic, wanted to start and build a new medical school with Case. But he said, I don't want to build just another medical school. I believe we're at a transition in how medicine is going to be practiced. Therefore, we better start and have a transition in how medicine is taught. And so he asked me if I would help him conceptualize sort of the world's first all-digital medical school, and we would build it from the ground up. This was sort of near the end of my tenure at Microsoft, where I ran all the research. And one of the things that we'd been involved in for many years was the development of this HoloLens thing, which at that point was not yet public. And this was 4 years ago. But the idea that I came up with first was that we would attempt to use this mixed reality capability with the HoloLens as its realization, and use the engineering school and the medical school at Case to develop this whole new curriculum. And one of the first things we decided to focus on was to teach anatomy using holography. So in fact, this medical school will have no cadavers. And everything about anatomy will be taught this way. So I'm going to just play this minute because it gives you the context, and I'll point out some stuff when it's done, or maybe as it goes here.
The HoloLens is absolutely the most amazing piece of technology. Within 5 seconds, I realized that the world had changed. It was an immediate realization that this is something exciting and we have to be a part of this. Seeing things in 3D is something that you could do before with some glasses. The thing that the HoloLens gives you is the ability to walk around those 3D objects and to really experience them as if they're in the room with you.
It is augmented reality, it is mixed reality. And what that means is I still see you, I still see this room and everything around me, but the digital content is inserted into the room as if it's actually there.
As a teacher, I can see what they're all looking at. And that's something that we think has real power.
It's actually opening up our interactions with each other.
The biggest drive is getting the anatomy curriculum completely done by the time we move into the new health education campus.
Today, we and the Cleveland Clinic are constructing a state-of-the-future health education campus. Our students will learn using the most forward-looking educational programs. HoloLens is a key part of this.
The actual act of dissection hasn't changed in generations. We have to be much, much more effective and efficient.
The biggest thing about medical school is there's just so much information and so much knowledge you're being asked to learn.
HoloLens is going to enable us to teach in an integrated way and to look at the body in ways they haven't been able to see it. It's sort of having X-ray vision, seeing through the skin.
My mind was just kind of blown. When I tried it on, it was perfect. It's really hard to understand what the anatomy and book's trying to tell you. So with the HoloLens, we can literally show you what's happening with the body.
We can look at how the heart moves, or look at how the brain processes information and how information flows around in our brain.
They can see when the heart valves are closing and hear the sounds.
How the diaphragm moves, when the lungs move. A click of the fingers is going to allow students to see how everything's interconnected in the body.
We have means to draw people's attention to things to get them where they need to look. Do you want to look and then pull the bones out?
And what they really crave is learning anatomy in the context of what they need to know clinically. What are they going to need to know for their clerkships and their future careers?
With HoloLens, we can have essentially any disease that you want to see.
So when I see an image like this in the hospital, I know exactly what's going on. This is how to treat and diagnose them.
The HoloLens provides like a new way of teaching anatomy. It can really speed up the process of learning this material.
I think HoloLens is the next big transformative change in medical education.
So as you saw in that model, the things that they built kind of look like the things you see in textbook. They're sort of anatomically perfect. All right? In fact, they almost look like plastic. And in fact, to teach the anatomy course, they've spent 3 years combining computer scientists, radiologists, those images, and then they give them to artists, and the artists essentially make them canonical. And that's fine for teaching anatomy, but I knew that part of that process started with a set of software tools that they had developed in order to take real CAT scans of human biology and then use it as the basis of creating some of these things. I had a different goal in mind with my wife, which was I didn't care about plastic-looking, meta models. I wanted the actual model of my wife because, in fact, what I was worried about was the anatomically unusual features, the individual thing. And so the idea was to take the tools, ask my buddy, the guy at the beginning of that video, Mark Griswold, if he would take his tools and, with some manual tuning, build a model quickly of my wife, and I sent him the CAT scan. And so what you're going to see here, in fact, that's a picture of it in my living room, is my wife's midsection. And I'm going to now show you live in this thing, that model, which is actually sitting right here, which you can't see without the goggles, but I'm going to make it such that you can get an idea of you just have to bear with me for a second. Okay, and just so you know, there's a 5-second latency between the headset and what you see on the screen. But as you'll see now, this headset has a camera that's taking the real world. That's why it's called mixed reality. So if I look up there, you can see it. You see my hands move. But if I look over here, what you'll actually see in 5 seconds later is my wife's midsection floating in space. And she used to call these parts her private parts, and now she calls them her public parts. So when they built this, they built this first model in order to be able to, first I built the model, one, to try to help the docs, and two, I had to convince them that this was actually interesting. They actually had no idea. When I said to them, hey, I have some technology that might be interesting and helpful to you, would you take a look at it? And so I set it up in my living room, and the head surgeon came over, and I showed him this model, and it took about 10 seconds before he was, completely, positive about the experience. Now, what it is, it's set up as a slideshow, and I'm going to click through it. And so what happens here is I now took all the muscle and skin and fat layers off, because once you make this into a software model, everything can be done. Then we color code each organ in some false color kind of model. Oh, lost it there. I may have to start again here. Okay. This thing has to register itself in space continuously to show you these models. So let me see if I can. Yeah. Yes. Well, I mean, I don't know in their weaponry, but this is. So anyway, now on the front of this, and this is important relative to the breast comment, is their intestines, which the doctor asked at the last minute that they add. And you can see how rough they are. And the big purple thing on the top is their liver. The problem, of course, was bladder cancer. And so as I take away some more of these things so you can see it, they made the intestines translucent so that he could see through them. And then you get down to basically the skeleton. The big yellow ureter on the right is swollen because it couldn't drain. This was taken on the day of the diagnosis. What I want to show you here is this big blue thing that you'll see in a second is her bladder. The thing where you see the dot on the side, the tan thing, that's the tumor. And interestingly, with these things, I can actually go in and just cut into the thing and look inside the bladder. And so there's the tumor on the inside, which is where it started. And up near the top of the little tan tumor, you see the hole, which was the ureter that the surgeon couldn't find. So if he had this before he did even the first procedure, she would have avoided 2 more operations. And so, this was model number 1. So the next thing, so what happened next is, I'm going to stop this for a second. The next thing that happened was the surgeon says, wow, that's really terrific, but I want more, all right? So he says, could you make the model, could she be laying down, supine? Because he says, what I've realized in looking at this model is my brain can now have its own mental model. Just as Dan thought, I can show you something, your brain remembers it. What's interesting is that all the slices of a CAT scan, you can spend your life as a radiologist or a surgeon who looks at those things, n times a day. Your brain never integrates those 1,000 slices into a mental model that the rest of your human faculties can remember or reason about. Each slice is an independent thing. So then he said, hey, how about the vasculature? I'm going to be in there operating, and I got to worry about the blood vessels. And then he said, oh, by the way, could you make it from a new CAT scan? Now that we've done the chemotherapy, I want to see what happened to the tumor. And so we went on. And so my friends in Cleveland accommodated us one more time. And you can see all these things are just being pasted in the air. So this is the second model. And sure enough, they did all the things that were asked for. So here's my wife. She's now laying down. The red and blue things you see up here at the top are the veins and arteries. You see the 2 kidneys, which in her case, are actually, they kind of lay at different angles. One of the big questions that they had to ask was the thing you see in the middle here that's pink. Just below the bladder and near the tumor is her uterus. And a big question, because this was already deemed to be stage 4 cancer, was had the tumor metastasized into the uterus. And what they realized by looking at this is that they could just walk over here and look in there, and they could see that they don't touch. And that saved her uterus. And this also was a model like the others where they could subtract things away to make it easier. Another thing that's fascinating about this is you see this blue thing looks like a little straw. That's actually the stent that got put in her 3rd operation, the 2 of which we wouldn't have had to have if we had this. And if I look inside this kidney, you see the little loop in there. That's the end of the stent that keeps it from being pulled out. And if you go down to the other end and you actually look inside the bladder, there's the one in the bladder. So they know exactly where it's sitting as they begin the operation. And they can look at the tumor, which in fact has a slightly different look to it now. You can see it's rougher and thinner around some of the edges. But unfortunately, that also showed what the limits of the chemotherapy were, which was not very effective. And so this is sort of the old model. So they could do comparative analysis, but they made it lay down. This is one that just focused on the blood vessels. They added the blood vessels to the first model you saw. And that's holographic imaging. So the So in fact, when I showed it to the surgeon, I didn't want to sort of embarrass them, but I have a movie taken through the HoloLens just like this, when they actually were doing the training the morning before, the day before her surgery, and they're like kids in a candy store. They said, I mean, literally, the robot operator said, this is, without a doubt, the coolest medical imaging of any kind I've ever seen. Can I have this hooked up to my robot like tomorrow? And unfortunately, my answer to this was, well, maybe in the future you can, but making this economical and easy to do is hard. And it's hard because for it to apply in this kind of application, it can't just be one instance like it has to be for the anatomy teaching, all right, or even a handful of instances. To have this kind of utility, I have to be able to take a CAT scan of anybody, and instead of having this slice that you can look at, like you're playing a video game where your brain doesn't really integrate it. When the surgeon looked at this, a number of things he said was he had to decide that since they're going to remove her bladder, he's going to have to hook her ureter up to an ileal conduit. And he said one of the things you almost never know when you start one of these procedures is whether the ureter is long enough, because everybody's ureter is a different length. He said, looking at this model the night before, he says, I knew without a shadow of a doubt it was long enough. He says, I slept better the night before the surgery because I didn't have to worry about the unknowns because I could see them in my mind. And so, what are the challenges? Well, just based on what you saw, on the left is what this looks like without manual editing. When he, very late in the cycle, asked in the first model for the intestines to be added. Well, that's one of the most irregular and complex elements of all those organs in the abdomen. And you can see, if you really squint at it, you can kind of see it running around and folding back and forth just like the small intestine does. But it has all kinds of artifacts on it that probably aren't really there. And that's because that part was done 100% by software, but of the expert system flavor. Now the other parts, that look really smooth and pretty clear, like the kidney and the bladder, they know that those things are, anatomically smooth. And so they have a tool, sort of like Photoshop, for 3D stuff, where they can smooth and hint to the computer, well, that didn't have like little spikes on the side of the bladder. And, but what you really want for this to be useful, for example, to be able to do that decision about was the uterus in contact with the tumor or not, you want accuracy, all right? The tumor, one could say, if you were just doing this based on what you thought a normal, bladder looked like, well, the tumor would be an artifact and it might get removed. But that's what you want to see. So in a sense, this is why I'm now very intrigued with this idea of how machine intelligence could make this all a reality. And it comes back to what I said earlier about, this asymptote we reach with expert systems, which is eventually even if we think we know the problem, the test for whether someone really knows the problem is to say, okay, write it down as a piece of code that does everything that you do. And then you realize how quickly they fail, or we all fail. And so the trick is to, I think, attack this thing a bit more like attacking Go. But try to, the game here has got a much more complex rule book that has to be learned. So, if you read the thing that was on that the Google clip from DeepMind, A lot of the problem in applying machine learning and artificial intelligence in these spaces is there is no big data from which to learn. And arguably, the AlphaGo Zero experience might even argue that I'm not sure I want that data. Those humans, they really don't understand it that well, all right? And so maybe it should be learned and how to do that. So I wrote down these things that I think I'm going to continue to work on, which is first, how to learn to discriminate the tissue types. It turns out that the CAT scans and the MRIs, this was all one CAT scan, each thing you saw. It turns out we can composite MRIs and PET scans on top of these things, because once they're all just aligned, that's a pixel problem. So that's the second thing, is if I want more and more resolution, I want to take all the imaging modalities and I want to combine them, and then I want to let this algorithm learn on that. I want to learn how to remove artifacts without removing important details or masking diseased tissues, because that's why we're doing this in the first place. And ultimately, I want to learn how to do this with video imaging and animations, so that we do have imaging systems like the one that you saw in the Cleveland Clinic video of the beating heart. We can image beating hearts today, but that just gives you a gazillion more images that you have to composite and hook together and then figure out how to animate. And so I think, frankly, that many of these are approachable without having to get to generalized machine intelligence. This doesn't require some higher order purpose. But similarly, it's not going to happen in this case by somebody thinking that they know how to write or give us data sets from which to train, because this is about N of 1 medicine. And so in a sense, we must get to some kind of transfer learning, where once this thing has learned how to find a bladder, because it sort of ought to be here, and its tissue ought to respond about like this, it can basically figure out what the bladder is, but then realize that there's something else in this thing that doesn't exactly look like a bladder, and therefore it must be a diseased tissue, and then color code it differently. And if we can do this, then I believe in the relatively near future, when you go in and get any imaging done, the way it'll get delivered is it'll just be a digital file like it is today, but you'll view it with a thing like a HoloLens and not sitting at a computer monitor flipping through things like a cartoon. Thank you.
So we have time for probably one or two questions. Do you want to? This one's close.
And then also,
ask so everybody else can hear you.
Okay. Could you do this live as the surgeon or the robot is doing the surgery with instrumentation? And then also, can you separate like the vasculature of the heart, because the heart's always beating without stopping it, because that, you have to have a blood-lung machine. And could you separate the vasculature within the heart at the same time, so you can separate those two movements from each other?
Well, I'll just give you the general answer, which is...
And then also, could you use contrast agents?
Just like the doctors, she just wants more, all right? The answer is, as the computers get bigger and bigger and bigger, the amount of time it takes for them once they understand how to do this. The magic thing about the models as they are today is, if I want to train something to recognize just one feature and I have lots of things to learn on, it may take me, the biggest computer on the planet, a week or a month to build the model, but the model can run in real time on my laptop, all right? Because you're building a model, you're not redeveloping the model every time. So that's just why a human can just look at that thing and watch it beat or move this thing or look at an image, and if you could see it in real time, the human could process it in real time, because it understands and it does all this stuff in parallel. So I think there's not a reason that the computing will be a problem. On the other hand, even today, to make this interesting, you need very high resolution imaging, all right? And today, the only way we know how to get that is that, we put you in a big old machine in a tube, and we run that thing around. So like when people do PET scans or MRIs, like when they're doing brain surgery, I've been in operating theaters that have, they have the CAT scanner or the MRI machine here, and they have the operating table on wheels here. And when they want to check something out in the middle of the operation, they wheel you into the machine, all hooked up, and then they run the CAT scan and they bring it back. And so, I mean, once we have the computing capability, then it's sort of back to the imaging guys, to figure out, okay, well, how many ways can we rig up the imaging such that it could approximately be real time, or, how do you operate? I mean, we don't know the answer to those questions. But because today, 4 years ago, people thought it was going to be a miracle that we could do this statically even to teach anatomy. And that's clearly a slam dunk now, all right? And, the fact that my buddy made those 2 models over the weekend, by hand, just with the tools that they had been developing for model building, I think, demonstrates that it has unbelievable potential. But if you want it to be done for everybody, my wife, when she saw this, I'll tell you one other story just quickly. It's because it's very interesting. When the surgeon came to see that thing in my living room the first time, my wife was wearing the other headset. And when we have 4 of them, and 4 people can interact with this thing like it was there together in real time. So the surgeon looked at it, and then my wife was looking at it, and he started to explain to her her own anatomy. She's an artist. She wouldn't have known her kidney from her liver, all right? And after 10 minutes, of him explaining this, he said he just wanted to keep studying it, and she said, okay, it's great. But it was a qualitative change in my wife's view of her own cancer, because she now understood where it was. She'd seen the tumor. She understood it went through the bladder wall. She understood why it was going to have to come out. She understood what had happened and not happened through chemotherapy. That all happened in 10 minutes. The next day, she had her quilt friends over, and they were all talking, and she put the headsets on the quilt club, all right? And she gave a complete tour of her own anatomy and explained the cancer and everything about where it was and why her ureter was swollen and what was going to have to happen. She learned all that in 10 minutes. And she can quilt too. But I'm just saying, everybody has this ability to learn visually is so powerful compared to all these other mechanisms that it's good for the patient, it's good for the student, it's good for the practitioner. Okay, I'm sorry.
So,
we'll do one more quick question if we can.
have you thought about using technology like the CAPTCHA technology that they use, when people are authenticating for graphics, and now they use it for the automatic cars to recognize signs, or is the tissue too specific to be able to use some of that technology? And then the second question is, how's your wife doing?
Thank you. The signs and that kind of stuff, that's just toys. I mean, that's no problem. That's a solved problem. I mean, you understand, machines are now conversational. They recognize images. We teach, at least when I was at Microsoft, we teach computers languages now by just giving them texts to analyze, all right? And when we want to teach it how to translate, like from Chinese to English, we just give them, 1,000 texts that, in English and Chinese that are nominally equivalent. It learned how to translate, all right? So, I mean, that level, is pretty amazing already, but that's not enough to do this. So that's why I say those are kind of one at a time deep neural networks, but they, in my opinion, are not, I can't solve this problem because there's not a zillion images of my wife from, to learn from. And so, if I just smear all of the bladders of the world together and say, hey, figure out what a bladder is, well, it says, okay, I know what a generic bladder might look like, but how do I know what that one looks like? And so, and there's just so many inputs here. The tissue response from the CAT scan and from the MRI are each different. That's all data. But when you're trying to composite it all together, it's kind of a difficult problem.
So let's thank Craig.